Hello, today we're looking at our last lesson in Unit 8. We're talking about application problems related to parametric equations. In algebra, we explored how things are connected or related through similarities and differences. We've looked at functions and relations to find input and output values. However, there are some situations that need a different approach. For example, let's consider when a hurricane is heading toward the southern United States. The closer the storm approaches the coast, the more gas and bottled water is sold. Suppose for every 100 miles the storm moves that a convenience store sells X gallons of gas and X squared bottles of water. Algebraically, that relationship would be written as follows. The bottles of water is equivalent to the gallons of gas squared. Even though this is correct thinking, it's misleading. The equation implies that gas is changing the demand for bottled water, when really it is the proximity of the storm in miles to a region that changed both items. It would make better sense to write two separate equations where we considered either miles from shore or time as the changing parameter. We could write two separate equations to model the situation. The gallons of gas equals miles minus 100, and the bottled water equals miles minus 100 squared. In this way, you can see that miles from shore is the cause for changes in the sale of gas and water due to the impending storm. Parametric equations help us look deeper at hidden parameters that affect change. Parametric equations are used in two ways: to find a graph of modeling an equation and to simulate the motion of a projectile. So let's jump in. This one we're going to use our graphing calculator and set the mode to parametric and then graph it. So let's open up our calculator. In the menu on your graphing calculator, you can go Menu and number 3 and Parametric on the TI Inspire. We're going to graph t plus 1 as the first parameter, and then we're going to graph t squared minus 3 for the second. They want us to go from 0 to 6.28, and if I go back to the tab, you can see that the time is from 0 to 2 pi and the step is 13 hundredths. So looking at the graph, you can tell we have half of a parabola. So putting that on paper, we've got from 1 to negative 3, where the vertex is. And it's going that way. And the path went from the vertex upward. The settings we said were from 0 to 6.28, which is 2 pi, and the step was 1300. So they want us to investigate what changes to the graph occur if we did a t minimum of negative 6. So if we go back to the tab and a t minimum was negative 6, what would happen to our graph? And you can see what happens. It allows us to view the entire parabola or the entire curve by showing negative time values. So that's what happens, or what changes occur. It allows us to view the entire curve. Then if we show that in a different color on the other screen, we have the entire parabola. Next, they want us to know what happens if we change the t-step from 13 hundredths to 5 and explain that. So let's give that a try. So once again, hitting the tab button and back to that graph, we're going to change the time stamp from 13 hundredths to 5. and we've got straightened out lines. And what would that indicate for us in terms of the graph? Can you put something into words there? I would say something like this. This records an XY value every 5 units of time. It straightens the curve because time steps up in larger increments or values or sections. Let's consider a circle with the radius of A, and it rolls along a horizontal line. As the circle rolls along the line, there's going to be a point P on the circle that will trace out a curve, and that curve is called a cycloid. That's this blue curve. Cycloids are used to solve problems that involve the shortest time. When the radius of the circle is A, the parametric equations of the cycloid are given by these two general forms. We won't do too much with cycloids here, but it is fun to graph one. So let's say we want to use our graphing utility in parametric mode to graph a plane curve that's represented by these equations. And we're going to use a viewing rectangle from 0 to 60 and from 0 to 8 on the X and the Y. And our time will be from 0 to 6 pi with the normal t-step. So that way we can take a look at this cycloid. So we want a parametric equation, and our X value is 2 times t minus the sine of t. And then our Y value is 2 times the quantity 1 minus the cosine of t. And we want the time to go from 0 to, 6 pi, 0 to 6 pi. Get rid of the 6.28. Keep the t-step the same. And we're going to make our window. They wanted us to go from 0 to 60. And then the Y was going to go from 0 to 8. And take a look at that. Okay, so we say okay to that. And there you can see we get 3, we get 3 iterations of that cycloid, and you can sketch that on your paper if you'd like. Example 3, let's say a baseball is hit straight up from a height of 5 feet with an initial velocity of 80 feet per second. We want to write an equation that models the height of the ball as a function of time. So if t is our parameter, then the position of a baseball is going to follow gravity with feet per second. So gravity, the position is 1/2 gravity times time squared, plus initial velocity times time, plus our initial starting height. So that's our position function. Half gravity is pulling us on to the earth at 32 feet per second per second. So half of 32 is 16, so negative 16 t squared, and initial velocity was 80 feet per second, and our initial starting height was 5. This is our S sub 0, this is our V sub 0. Okay, so using that algebra equation for vertical motion. So this is our position, and if we go to our calculator, we want to use parametric mode to simulate that pop-up. So our equations for x of t would be t, and our y of t would be negative 16 t squared plus 80t plus 5. So let's go graph that on our calculator and make the settings from 0 to 7 on x and 0 to 120 on y. So my equations look like this in the graph window, and I've set the window settings from 0 to 7 to 0 to 120, and we've got this kind of action. So we want to use parametric mode to graph the height against the time, and we want to figure out how high is the ball after 4 seconds. Now on my calculator, I could either trace that, or I could use the table and look at the time stamp at 4. So how high is the ball would be the y value, and it looks like that's 69 feet when the time is 4 seconds. So we've got quick sketch here. So we have the ball is at 69 feet after 4 seconds. And then our last question is, what's the maximum height of the ball, and how many seconds does it take to reach that maximum height? Well, we know from parabolas, if we knew the vertex, we could use that equation, and the vertex is half is opposite b over 2a. So that's the x coordinate of the vertex. In this case, we don't have an x, we have t for our time parameter, and the b is 80, and 2 times a is negative 16, so 2 goes into 80 40 times, and then we could reduce that down, 40 over 16, and that gives us 2.5. So we know the vertex happens when time is 2.5 seconds. That's our x coordinate. So 2.5, and again, I'm going to go let the calculator do the work for me, and we can look at, get off of there, whoop, lost my picture now. Undo the table, and I could either let it trace for us and go over to 2.5. I'm watching this little dial down here. See how close it'll get us to 2.5. 105 feet. So the maximum height would be 105 feet when the time is 2.5. So at 2.5 seconds, the ball reaches a maximum. And that was 105 feet in the air. In this next example, Sammy hits a ball when it's 4 feet above the ground with an initial velocity. The ball leaves the bat at a 30-degree angle with the horizontal and heads toward a 30-foot fence that's 350 feet away from home plate. We want to know if the ball clears the fence. So in this case, I'm wanting to write x as a function of time using the fact that we've got velocity, it's 120 feet per second, but it's being hit at a 30-degree angle, right? So I've got that the x value is cosine, so x is 120 cosine at 30 degrees times t. And our y value would be the position formula, so negative 16 t squared, and then vertically we would want sine to be the vertical, so 120 sine of 30 degrees times t, and the ball was hit from 4 feet above the ground, so that would be our parametric equation. Now let's go on and graph those with our calculator and take a look at what happens there. So my picture is going to look like this. The equation was entered 120 cosine 30 degrees times time for the horizontal distance, and negative 16 t squared plus 120 sine 30 degrees times time plus 4 for the vertical distance. So we want to know if the ball is going to hit the fence or not. And the fence was, 350 feet from home plate. So I guess we could trace that. Trace along there. And come out here to where it's coming down. Well, right in there, the ball's at like 23 feet tall, 27 feet tall. So the ball is going to hit the wall. It appears like the ball's going to hit the wall. So I want to look at y at about 3.37 seconds. I believe I figured that out. So right about 3.37 seconds, the ball is 24.5 feet high. And if the wall is 30 feet tall, then the ball's going to hit the wall. So you could put something into words. How do you know that? The other key fact to know is what the horizontal distance is. That's where I got the 3.37. I needed to go out to 350 feet and check the height, and I could do that just by tracing, and found out when we traveled 350 feet, the height of the ball was 24.5 feet tall. That meant that the 30-foot fence, the ball is going to hit the fence before it hits over the wall. 24.9 feet high at 350 feet away. If so, by how much does it clear the fence? If not, could the ball be caught? Well, we know it's not catchable since it's higher than a person can jump. It'd be pretty hard to jump 25 feet tall. I said 24.5 feet high. It's not catchable. It's too far over their head for a normal jump. And then here's our last example. Denise hits golf balls off the tee with an initial velocity of 80 yards per second with her driver. And how far down the fairway does the ball hit the ground if it comes off the club, making a 20-degree angle or a 25-degree angle? So in either case, we need to have an equation. So x is going to be 80 cosine theta times t, and the first one we'll use 20 degrees for our theta. And y is negative 16t squared plus 80 sine theta t, and it's being hit from the ground, so the ground is our initial height of 0. So if we want to know, let's see, when it's going to hit the ground, we'd have to solve this second equation, the y equation, for 0. So when y is 0, that would be our question. We could factor out a t. So 0 is t times negative 16t plus 80 sine theta. So t is either 0, well, that's before she hits it, or t is 80 sine theta divided by 16. And that would be, let's see, 16 divides 80 5 times. So when t is 5 sine theta. So we could have a general formula. Let's go to a new piece of paper. So our third step, we could say x is 80 cosine theta times time, and y is 80 cosine theta times, would we have 5 sine theta? So a general formula, 80 times 5 would be 400 cosine theta sine theta. So this could be our general formula to calculate. And question A asked us what would happen if it was a 20-degree angle off of that club head. So the y of 20 degrees would be 400 cosine 20 times sine of 20. And going to our calculator, let's figure that up. So 400 times cosine 20 sine 20 looks like it goes 128.56 yards. And then the last one, if we just copy and paste this, and substitute 25 degrees in there, the ball travels 153.21 yards down the fairway. So 20 degrees, whoop, that was not good. 20 degrees, the ball goes about 128.56 yards. And then 25 degrees, doing the same thing, 400 cosine 25 times sine of 25. The ball travels about 153.21 yards down the fairway. And that, my friends, finishes Unit 8 on conic sections and analytic geometry.